All right. Oh, catalyst. That was we already went over that. That was the last chapter. Okay. Equilibrium. Equilibrium is the way is what we refer to as the term we use for when reaction has stopped changing the amount of reactants or products. So when you mix two things together, uh, and they start reacting, and the amount of reactants goes down, and the amount of products goes up. Okay, when you do that, eventually, the amount of reactants that goes down is going to stabilize. The amount of products that's going up is going to stabilize, and eventually, you're not going to lose any more reactants. You're not going to gain any more products. And it will appear at that point that the reaction has stopped. I'm putting stopped in air quotes here for a reason. We'll talk about why. Um, and what is actually happening is the reaction has not stopped. Okay, it actually continues on and on and on and on forever, which is this dynamic thing, which we'll get to in a moment. So equilibrium is the term we have for when a reaction has come to this point where the concentrations of the reactants and the concentration of the products are not changing. Okay, it's when they've reached a standstill or a stalemate. Um, what we now believe, and this is the most important word in the entire chapter. They used to think that when the amount of reactants went down and the amount of products went up, they used to think that the reaction did in fact stop, where no more reactants were turned into products and no products were going backwards to turn into reactants. But now we actually believe that equilibrium is a dynamic process where reactions actually never actually stop until you would work them up. We actually believe what happens is that the reaction goes on and on and on and on and on forever and ever and ever, as long as it were in an isolated system. You didn't get in there and work the reaction up. It's just that we believe when equilibrium is reached, the rate that reactants turn into products is the rate that products are turning back into reactants. So you'll notice we have a new arrow here. This is our equilibrium arrow. This is going to take some getting used to for you guys. This equilibrium arrow, so instead, up until now, in Chem 101, we always just used a single-headed arrow, meaning that reactants turn into products, right? And the reaction only goes in that direction. Okay, but now we need to accept the fact that reactions are reversible. Reactions can and do go backwards. Products can break back down and turn back into reactants. So that's what this double-headed arrow here is for. It's a half arrow in the forward direction and a half arrow in the reverse direction. Okay, and that is to indicate that this reaction is reversible and can go backwards. Let's see, what was I going to say? Let's talk about this dynamic thing. What we believe is if I had all this stuff in a box and it was an isolated system, nothing gets in, nothing gets out, that if I started with only reactants, the reactants would start turning into products and I would start to lose reactants and gain products. So reactants are going down, products are going up. Okay. But eventually the concentrations will stop changing where I have this much reactant left and I get this much product. And at the macroscopic level, it will look like the reaction has stopped. But what we now believe is at the molecular level, the reaction is still going on and on and on and on and on feverishly. So how is that possible? Well, the only way that this is possible is that when equilibrium is established, when the concentrations stop changing, the rate that reactants are turning into products must be the same as the rate that products are turning back into reactants. We say the rate of the forward reaction must be matching the rate of the reverse reaction. They must be equal to one another. It's a crazy concept to think about, right? But you got to think about it like this, if I'm turning two reactant molecules into product at the same speed that I'm ripping that same product back into two reactant molecules, at the macroscopic level, you won't notice a difference, okay? Because the amounts of everything are the same. Best way that I have to think about this is if you could imagine two cities connected by a bridge, right? The number of cars in each city would be constant if the number of cars leaving this city was happening as the same at the same rate as the number of cars leaving this city. So maybe we could end up with, you know, we could end up with 800 cars in this city and 300 cars in this city. And you could still have cars going back and forth, but if 15 cars are leaving this city at the same time that 15 cars are leaving this city at any given moment, you still have 800 in this city and 300 in that city. So that's what dynamic is all about. It's the rate, it's that, when a reaction has appeared to have stopped, what's actually happening is it's just the rate that reactants are turning into products is the same as the rate that products are turning back into reactants. So that's a really important term, this idea of dynamic, and the fact that we now have to try to use this new arrow, which is going to be hard. Like, that's going to be a hard habit to break, because up until this point, you haven't been using an arrow like that. So it's gonna be a hard habit to break. Okay, so now for equilibrium constants, we write what is called a mass action expression. So you're going to want to call this a mass action expression. And mass action expressions are the product concentrations over the reactant concentrations. Products over reactants. And what this comes out to is that if you take the concentration of the products raised to their exponents, we'll talk about that in a second, divided by the concentration of the reactants raised to their exponents, you will get a constant, okay, called the equilibrium constant. Now, we abbreviate that as a K with a subscript C for concentration constant, or a K with a subscript EQ. Both of those is fine. Both, KC or KEQ doesn't matter to me, whichever one you prefer. Both of those are totally fine. So the equilibrium constant for a reaction is equal to the product concentrations divided by the reactant concentrations. Now, the coefficients that are in front of the products and the coefficients that are in front of the reactants, they become the exponents that you raise those concentrations to. So this is kind of like, to make a connection here, okay, remember we said in the kinetics chapter that if you study the mechanism of a reaction, you can write the rate law from the slow step, the RDS, right? The rate determining step. And if you know the slow step, the coefficients become the exponents, right? So it's a lot like that. Only this time it's products over reactants, and with the rate law, it's only the reactants that go into the rate law. But with a mass action expression, it's products over the reactants. So let's practice writing some mass action expressions. So let's write the mass action expression for this guy. So that's going to be, we start with Kc or Keq, doesn't matter, right? Kc or Keq. And it's the product concentrations. So it's going to be the concentration of NO2 raised to their exponents to the fourth times the concentration of O2. That's got a coefficient of 1, so you don't have to put anything there. You could put a 1 there if you want, but you don't have to. So products on top over the concentration of the reactants, N2O5, okay? And then that guy's going to get squared because there's a 2 there. So there's our mass action expression for this top reaction. Why don't you write the mass action expression for the bottom one here? Cool. So this is going to be Kc or Keq, doesn't matter which. And it's going to be the product concentration, so carbon monoxide to the first times H2, and that guy is going to get squared all over CH3OH, and that's got a coefficient of 1, so that's to the first power again, just like that. Okay, let me give you another one. This marker's dying, so get rid of that guy. Let's try this guy. Very important reaction, which we'll talk quite a bit about, especially in Thursday's lab when we learn about Le Chatelier's principle. I'm going to write the mass action expression for that guy. N2 plus 3H2 goes to 2NH3. Right, it's gonna be the concentration of the product, so NH3 squared over concentration of the reactants, N2 times H2 cubed. So right now we're just practicing writing mass action expressions, okay? So it's products over reactants, and coefficients always become exponents here. Awesome. So now what I want to do is I want to talk about what the constant, so when you plug the concentrations in here and you solve for the constant, I want to talk about what does that constant tell you about the reaction. Yep. Okay, so imagine like this top reaction. Why don't you go ahead and write the mass action expression for that top reaction, that synthesis reaction between hydrogen and bromine, H2 plus Br2 goes to 2HBr. Go ahead and write the mass action expression for that. All right, so this reaction has a mass action expression that's HBr's concentration squared over H2's concentration times Br2's concentration. Okay. And if you look it up, this reaction has an equilibrium constant of 1.9 times 10 to the 19th. So this equilibrium constant is 1.9 times 10 to the 19th. So what does that mean? What does a number like that mean? Well, it's really kind of simple if you can just remember one thing. If you can remember that at the end of the day, it's product concentrations over reactant concentrations, then there's three possible scenarios that can arise. Okay? If you have an equilibrium constant that is way greater than 1, then what that means is that your numerator must be bigger than your denominator. How do you get a number that's greater than 1? Well, the number in the numerator must be bigger than the number in the denominator. Well, if it's way greater than 1, and by the way, we're going to define that as greater than 1,000 here in a second, but if your equilibrium constant is much, much greater than 1, then that means once equilibrium is reached, you have way more product than reactant, okay, present. So you got a lot of product, very little reactant. So what that means is the product side is favored. And that's what's going on with this reaction right here. This reaction has a huge equilibrium constant. So that means when this reaction reaches equilibrium, by the way, you have no idea how long that's going to take. Okay? The equilibrium and kinetics are two totally different things. So this reaction heavily favors the product side whenever it gets there. How long is it going to take to get there? I don't know. You got to do a separate kinetic study, which is the chapter we just finished up. Maybe do the initial rates method, right? Something like that. You can study the kinetics for the reaction. Okay, but all that this tells us is that when this reaction reaches equilibrium, there's going to be a whole lot of product and very little reactant. Okay, so that's what's going on with this reaction. You get a big equilibrium constant like that, product side is favored. You're going to get a great yield when this reaction reaches equilibrium. It's going to be like all product, no reactant. The other option would be something like this. Say that this equilibrium constant was 1.9 times 10 to the negative 19. Well, now that's an incredibly small number, right? That's like 0.000, right? 18 decimal point, 18 zeros, and then a 1 and a 9. Really small number. If you have a really, really, really small number, if that equilibrium constant was way, way, way less than 1, then what does that mean? Well, that means that you must have a bigger denominator than a numerator, right? How do you get a really small number? Bigger number on the bottom, smaller number on the top, right? So this means that, look what's on the bottom, reactants. If you have a really small equilibrium constant, this reaction would favor the reactant side. So the reactant side is favored. Sometimes we'll say if the reactant side is favored, we'll say the equilibrium lies to the left. And going back, when the equilibrium constant is greater than 1 and the product side is favored, sometimes we'll say the equilibrium lies to the right, right? Lies to the right side of the arrow. Final option is obviously, what if the equilibrium constant was really close to 1? Well, if you have an equilibrium constant of 1 or something really close to 1, approximately equal to 1, then what does that mean? Well, that means that your numerator and denominator must be about the same. right? And if your numerator and denominator are about the same, then that means this reaction doesn't favor either side. It means that when equilibrium is reached, you're going to have like a 50-50 mix of both reactants and products. So if the equilibrium constant is approximately equal to 1, then neither side is favored. Neither side is favored. Okay, and this you're going to have about a 50-50 mix of reactants and products, okay, if you have an equilibrium constant really, really close to 1. So this, what we just went over here, super duper duper important. Number one, can you write a mass action expression, right? Products over reactants. Can you remember it's products over reactants? Can you remember that the coefficients become the exponents, okay? And then tell me, in a moment, we're going to calculate these equilibrium constants, okay? Can you tell me when you get the equilibrium constant, what that means about the reaction? If you have a really big constant, product side's favored. Really small constant, like 0.00001 or something, reactant side's favored. And a constant that's close to 1, well, then that means that you have about the same amount of reactants and products when this reaction reaches equilibrium. Cool. Really important right there. Blah, blah, blah. Okay, so what is much greater than 1 and what is much less than 1? Well, the answer is about a factor of 1,000. Okay, so we consider much, much greater than 1, the product side being extensively favored to be when that equilibrium constant is greater than 1,000. Okay, what do we consider the reactant side to be heavily favored? Well, when you're 1 divided by 1,000 or 0.001, when you're below 0.001, then the reactant side is heavily favored. If the equilibrium constant is between 0.001 and 1,000, then that means, okay, that the equilibrium constant between those two, then that means that neither side is heavily favored, and that when the reaction reaches equilibrium, you're going to have some of each. Now, if I have an equilibrium constant of like 500, that means there's going to be more product in there than reactant, but there's still going to be a bunch of reactant, right? Okay, and if I have an equilibrium constant of 0.05, that means there's going to be more reactants than products, but there's still going to be a decent amount of product concentration when the reaction reaches equilibrium. So that's what I mean by that. Now, if you get an equilibrium constant exactly of 1, then that means it is truly a 50-50 mix, essentially. Cool. So now I want to actually calculate this. I want you to give this a shot, see if you can do it, okay? Here's what I need you to do. I need you to write the mass action expression for this reaction. We actually did this reaction earlier. This is a very important reaction called the Haber-Bosch reaction. So I want you to write the mass action expression. And then here are the equilibrium concentrations. So somebody's run this reaction, allowed it to reach equilibrium at 127 degrees Celsius. That temperature does not matter. It's not important. Now, obviously, the equilibrium constant, okay, is only good for whatever temperature you're doing it at. So this, when you solve for this constant, that's only good for 127. That equilibrium, you can't use that same equilibrium constant for 50 degrees Celsius, right? Okay, it's only good for whatever temperature it was done at. But anyway, I want you to write the mass action expression for this reaction. I want you to plug the equilibrium concentrations in and see if you can't get the right answer. It is a little tricky when you got numbers in scientific notation and you got to square them and cube them and stuff. It gets give it a shot. See if you can't do it. Worst thing you can do is get it wrong. Let's go over it, see how you did. So first thing we need to do is write that mass action expression. So Kc or Kq equals NH3 squared divided by N2 times H2 cubed. And now we need to plug these values into that mass action expression. So Kc equals the NH3 concentration, 3.1 times 10 to the negative second squared divided by, and by the way, you don't actually need those parentheses. I'm putting those parentheses there because when you have a number in scientific notation and it gets messy, so that's just to make that stand out. But those parentheses at the top, you don't actually need to enter. People, put them in the calculator and they do a lot more parentheses than they need to, and then they end up getting wrong anyway. We'll talk about what parentheses I would actually enter in my calculator here in a moment. Next up, we need the N2. So that's going to be 8.5 times 10 to the negative first, and then times the H2 3.1 times 10 to the negative third and cubed. Now, when I put this in my calculator, okay, you have some options. Okay, you could get an answer for the numerator, write that down. Then you could get an answer for the denominator, write that down, and then you could divide. But I don't. Now, I got a lot of parentheses here. I don't put any of these parentheses in. Okay, when I put this in my calculator, the parentheses that I actually put in would be the denominator here. So if I was going to enter this in my calculator, I would enter this as 3.1 e negative 2 divided by the parenthesis 8.5 e negative 1 times 3.1 e negative 3. Oh, and you know what? I forgot to square that. Oh my goodness. Start again. I would enter this in my calculator as 3.1 e negative 2 squared. Okay, so squared, right? Okay, and then divided by the parenthesis 8.5 e negative 1 times 3.1 e negative 3 cubed and close parentheses. Because I want to get an answer for this, right? Like that's got to be one set thing. If you don't put those parentheses in there, your calculator would do this divided by this, and then it would multiply by this. You don't want that, right? So if you didn't do that, try to enter it in your calculator again. I'm going to enter it in, right? And we'll see what we should get here. You should get an equilibrium constant of looking like 2 sig figs. I got 37,950. We're going to round it to 2 sig figs, so 38,000. But again, I'll show you how I put it in my calculator. So I put it in my calculator exactly like that. So you can see that there for a second. Okay. So let's talk about what this means. Okay. Oh, before I forget, you are going to love this. This is like the one time in chemistry where you don't worry about the units. We do not put units on equilibrium constants. I know, it's crazy. I mean, we could, we just don't do it because they have no physical meaning. Because this would be molar squared divided by molar to the fourth. So that'd be molar squared on the bottom. So this would be molar to the negative second. But we just don't do it. You will not find in a textbook. If you did write, over molar squared, it'd be fine. But we just do not include units on equilibrium constants. It's pretty awesome. Anyway, so we calculated the equilibrium constant for this reaction. It's 38,000, right? What does that tell us? 38,000. Great. What does that mean? Well, that 38,000 is way greater than 1. It's greater than 1,000, right? So it's much, much greater than 1. What does that mean? That means this reaction heavily favors the product side. It means when this reaction reaches equilibrium, you should have a lot of product and very little reactant, okay, left over. Unless one of the reactants was in a huge excess or something, which actually looks like what was going on here. Okay, but yeah, that's how this tells us that the reaction favors the product side. If you're trying to get a good yield of product out of this, this is good news for you. The unfortunate thing, we're going to talk about this reaction quite a bit when we learn about Le Chatelier's principle before lab on Thursday. The unfortunate thing about this reaction is it's so painfully slow. Like you would get a good yield out of this, but it's so slow it's just not useful. We'll talk about two German chemists that figured out a way around that. But anyway.